Yeah, good morning, everyone. So let's continue with the second order bandpass filter. So we'll talk about the switch capacitor version of this second order bandpass filter. And then we'll talk about the switch capacitor second order low pass filter. Okay? Yeah, that's actually homework. So this second order bandpass filter, the transfer function is like this. Yeah, the magnitude model plot. Yeah, this minus 3 dB bandwidth. This is minus 3 decibel bandwidth is yeah, omega 0 divided by Q, right? So we implemented this one. Actually, we synthesized this transfer function into an active RC filter. So this is an active RC second order bandpass filter. So input Vi is applied there. Output Bo is taken from here, this node. So we need, actually this 10K is wrong, right? So yeah, this consumes too much current. So this one is actually minus V2. Oh no, actually this is V2. So this is just a non-inverting integrator of VO, right? If this is just VO, V2, this is actually there should be R there. So to implement a non-inverting integrator, we need an additional op-amp to convert the polarity. Okay. So yeah, we wanna convert this one into a switch capacitor filter. So we wanna implement auto-zeroed switched capacitor bandpass filter. Yeah, then see, I will convert all those resistors into a switched capacitor. This one, should be stray insensitive, right? Stray insensitive, auto-zeroed. For the polarity inversion, yeah, we can implement this multiply by -1 by switching by changing the switches. Yeah, by changing the position of phi 1 and the phi 2 switches, we can implement polarity inversion. So we'll use 2 op-amp, many switched capacitors. Okay. Yeah, so let's try to convert the first one, this one. See, so let's just see. I have a Vi here, so I wanna convert R1 into a switched capacitor. Yeah, this T1 equal, C1 equal T over R1, right? This R1 is here. T is the period of this clock period. Okay, then yeah, for this one pop capacitor, say I need to float it. This is C, one pop capacitor. I just connect it during by one phase only. Yeah, during by two phase, I will float this feedback capacitor. For this QR, yeah, I can implement this one by a switched capacitor. Okay, so this is my VO. Any questions until now? Nope. Yeah, this capacitor will be that T of 1.59 mega ohm, right? That's a C value. Okay, let's continue with this resistor. Yeah, it's the same actually. So I will implement this one by one, and then by two. So this capacitor is T over 159 kilo ohm, and then oh yeah, one missing, right? What is it missing? Feedback switch. I need a feedback switch for auto zero, okay? Yeah, so this one, yeah, it's easy, same thing. Yeah, this is my one pop capacitor, and then I have a feedback switch here, right? So actually, I will say this is V2, this is V2 plus V2. So I want to generate the V2 here, non-inverting version. Yeah, how can you do that? Polarity, change the switch polarity. So here, see, I will change, usually this is by 2, right? So then I just make, this is by 1. Yeah. And then this is by 2. So here, see, you can see, yeah, during by one phase, so this switch is on and this switch is on. Then, yeah, this voltage will be input offset voltage. So voltage across this switched capacitor is VO minus input offset voltage, right? And during by 2, say this switch is on, so this amount of charge, this minus charge will be transferred to here. This there will be some positive charge will be developed here because the same current flows, right? Current flows. Yeah, this voltage will remain at the VOS, and this voltage will remain at the 0. Okay. The amount of charge developed here actually accumulated there is the change of charge between those two, right? So the delta Q here equal the positive charge. This C is, I can say C2. C2 times VO minus VOS minus VOS, something like that, okay? Yeah, see, the charge during, at the end of pi 1, the charge Q was C VO minus VOS, right? The charge at the end of pi 2 for this C2 is C2 minus VOS, right? The change of charge on C2 is accumulated on this feedback capacitor, one part feedback capacitor, right? Okay. So because that one is only C2 VO, right? So, yeah, so then I can say, so at the end of pi 2 phase, so that's C2, I will calculate the capacitor here. This is CFV2. So this is CFV2, one part capacitor. Actually, this is not C2. CFV2 times VOT n plus 0.5. That's the end of pi 2. Yeah, let's just see. Okay, I don't want to derive equation here. So anyway, you know, this plus VO, this amount of charge, C2 times VO is added on this CFV2. So my V2 will increase if VO is positive, right? So it is a non-inverting integrator, okay? Question until now? No? No question. Okay, so this is a non-inverting integrator, which is V2 equal integration of VO dt. There will be some constant multiplied here. Yeah, to implement this one, we must be careful. Okay, so here's yeah, so this V2 voltage is input offset voltage during pi 1. So yeah, it has a valid output during pi 2. So for this switch capacitor, for this feedback resistor 159K, I must sample V2 during pi 2. Okay? So here's yeah, to implement that one, I have a feedback capacitor. This is a CT of 159K. Then I have I will sample it during okay. So I have to sample, I will sample this one during pi 2. Yeah, if I connect it, see, here is the feedback switch is there, okay? I will need some slight different way of connection. Yeah, during pi 2, this node voltage will be input offset voltage VOS of the first op-amp. Then I can sample the V2 at the end of by2 phase, okay? No, this is good. Then during by1, this charge, that charge is, let's just say, there is a plus charge, minus charge there, right? The charge Q will be just this capacitor, CSFB, VO minus input offset voltage, right? VOS1. Okay. So I need to pump this capacitor into this feedback capacitor such that minus Q must be developed there, because this is inverting integrator, right? There must be minus Q on the right hand side, plus Q on the added on the left hand side. Okay, so this plus Q must be added here, must be pumped there, right? Yeah, to that one, I need some switch connection, different switch connection, okay? So if I make a, let's just say, oh no, not that one. I need this kind of switch to perform that operation. So during by1 phase, so this plus Q charge is transferred to this node, right? Plus Q, right? Plus Q. And then minus Q will be developed there. Then I can perform inverting integration, okay? Question?
T 오버 1.5오메가 캡으로
Yes. Speak your question again.
그 위에 있는 캡으로는
Oh, you mean the question is the charge here, yeah, will transfer the some amount will transfer into this capacitor. That's your question, right? Yeah, sure. Yeah, it does. It does. Okay. So I'm just talking the polarity only. Okay. So this, yeah, some amount of plus Q will be transferred there and transferred there, right? So I'm just talking about polarity. So it must perform inverting operation, right? To perform inverting operation, I need the switches. I need to connect the switches like that. Okay. Okay. Then see, my auto zero has some problem. See, if I have if you look at this one, my auto zero got some problem. For this capacitor. See, if I have input offset voltage of first op-amp is there, then yeah, what's the charge? Yeah, this is too complex, right? This figure is too complex. So okay, let's talk about this. Yeah, let's continue. All right, this Q is like that. Okay, then yeah, this is at the end of I2 phase. That's a Q sampled in this CSFB at the end of I2 phase. Then at the end of by1 phase, by one base, then see what will be charged left here? Left the Q. Yeah, so let's see. This node voltage will be VOS1, right? This node voltage is what? This node voltage is VOS1. How about this node voltage is 0, right? So the charge Q will be CSFB times just VOS1, not minus VOS1, right? So the amount of charge, delta Q, yeah, this delta Q delivered is CSFB, the minus delta Q on the right-hand side, times VO minus 2 VOS1. So I couldn't accomplish auto zero operation for this switch. But see, if I have just integrate the integrating capacitor, I have a problem. But because I have a resistor here, so switch the capacitor resistor, right? So it will be amplified only a little bit. Because of this is a low pass filter. See, because this resistor and this resistor, the input offset voltage will be multiplied by, if this resistor is R something, R2. If this resistor is R3, this will be multiplied by R2 plus R3 divided by R3, R2, yeah, R3. So, because, oh yeah, then this is around 2, right? So, yeah, because of this resistor, my VO will have around twice input offset voltage here, okay, at the output. Doesn't matter too much. Question? No? No question? Okay. So let's try to simulate this one. Do I have some simulation result here? Oh yeah, this is the one, the nice figure. So, you know, this is a switch capacitor, second order bandpass filter. Oops. Yeah, so to implement a non-inverting integrator, this is a non-inverting integrator. Yeah, so I switch the polarity, switch polarity here, okay? Used to be by 2 for this switch, and then by 1 for this switch. I changed the polarity. So there will be a delay around the delay here, right? Because I sample V out during by 1 phase, and then I just generate a valid output during by 2 phase. Okay. Here, see, just by 1 phase is just bypassed directly, so there is no delay between here and there. Okay. Yeah, so yeah, for this one, I just sample this V2 during by 2 phase, and then to dump this plus Q here, plus Q here. I just make switches like that. Okay? Question? No question? Who didn't ask question? Robert, You didn't ask question for a while. Any question? No question. Then I can ask you a question then. So, do you have no objection of this switch connection? Do you have any objection? No objection of this switch connection? No? Okay. Yeah, then I think you can derive G-domain transfer function here. Okay? Yeah, how can you derive a G-domain transfer function? Yeah, here and here, see, I don't have any problem. Let's just see. Yeah, auto 0, and here, let's just see.